Good afternoon, everyone. Welcome to today's Yugabyte webinar on Replica in distributed nature and real-world examples. So I'm very glad that for today's session, we actually invite one of our partner, Airwallex, to share their story as well. All right. So to get started, let me just share my screen. Okay. All right. So for today's agenda, I will pretty much cover some technical stuff like the Replica overview, Replica, how does Replica actually design and architect in a more distributed fashion, and some of the best practices and improvement that we have made in the distributed world. And Harry that will then take over to share something on the real world examples that leveraging on replicas, for example, some of the business requirements, their database journey while adopting the Yugabyte, and some of the learnings as well. All right. So before we actually kickstart, just a quick introduction about ourselves as well as for the company itself, right? Maybe you guys are not familiar with Airwallex. So Harry will later on do a quick intro on the company as well. So just a little bit more of myself. My name is Ron. I'm currently the pre-sales in Yugabyte. And before joining Yugabyte, I actually was handling relational databases, data warehouses, and data platforms in different companies before. And feel free to get connected with me on LinkedIn, and we can set aside some time to free chat. All right. Let me hand over to Harry. Harry, you want to do a quick intro about yourself?
Yep. Hello, everyone. Can you hear me? My name is Harry Huang. I'm working at Airwallex at the moment. I have been with Airwallex for quite a long time, since 2016, basically from the nearly very beginning of the company. So my area is more about payment, forex, FX, and yeah, and on the engineering side, it's more on microservices and our underlying infrastructure of database, SQL, NoSQL, MySQL, everything stores data I touches in the company. So that's a little bit about myself. So I'll hand over to Ron to keep on going. Okay. I'll do a quick intro of Airwallex just in case you guys haven't really heard of it. Yeah. So Airwallex is a fully licensed and regulated fintech company. We provide services like multi-currencies for business account and forex, FX services, forex exchange, and payment processing like credit card acquiring and issuing, and we are a API first company. So basically, we designed everything from the API first point of view. All our services are accessible from API. And Airwallex business account actually allows our clients to collect and hold funds up to 19 currencies at the moment, and can transfer to over 180 countries in like 40 something currencies at the moment, because the currencies and country coverage is growing every day. So my data may be outdated. So you guys can check our website to see what's the latest state. And next page, I would like to share the coverage of our business in the world. So this is the map of the Airwallex business capability around the world. And as you can see, the coverage is pretty wide. So we basically do our business across all major continents, all major countries. Yeah, even in Russia, I'm not quite sure. We have some limitation recently to do the transaction. I think that's for sure. Okay. And this page is about our architecture. It's a very high level architecture. We provide a unified API interface that we already integrate with different liquidity provider, different FX provider, different local clearing system. So it's very tedious because every country, every region has their different legal requirement, their different licensing. So we actually have to get a license one by one and package it as a whole package unified API to our client, which provide a one-stop shop experience for our users.
All right,
okay, cool. I'll hand over to Ron.
Yep. So I hope now you guys have a better idea of Airwallex business. So for those who are not familiar with Yugabyte, so let me just do a quick intro on Yugabyte as well. So Yugabyte is just, you can treat it Yugabyte as a supercharged Postgres. So it's a distributed database for transactional workloads. All right. So it has a built-in resiliency, on-demand scale, and more. So it's a distributed Postgres, so you can literally lift and shift your existing Postgres applications and to enjoy the built-in resiliency, scalability, flexible disaster recovery. It has a full Postgres compatibility, right? And also it has because it handles data, so it has an enterprise data protection, like all the security functions. And we also have different deployment models. So you can deploy in your own environment, you can consume it as a service, or even build your own DBAS solutions, database as a service solutions. All right. So before I go into technical stuff, just want to let the audience know if you have any questions, any thoughts, any feedback, feel free to post in the chat. So we will address them. If I saw them, then I will address immediately. If not, then I will address them at the end of the session. All right. I want to keep today's webinar more interactive. So this is actually the fundamentals of distributed database like Yugabyte. So generally as you can see from the architecture perspective, it is very different from the monolithic relational databases. It is more like a clustered database, right? So the cluster itself can scale horizontally, right? Rather than just vertically, it can also scale horizontally, right? And for Yugabyte itself, generally it consists of two services. One is called the master service. The other is T-server service. So the master service is actually holding all the metadata and the configuration changes, more like what we call the orchestration, right? Then the T-server itself is actually the one that holds the data itself, right? So we also call it the tablets. They hold the tablets. So the tablets in this case, since we are the distributed database, where the data is written to a distributed database like a Yugabyte, the table is automatically sharded into multiple pieces. Like here you can see, it's just an example. Like the one table will be split into like 4 different tablets. 1, 2, 3, 4. Then for resiliency and HA purpose, for each tablet, it will have multiple copies. Here, it will have 3 copies. Of course, you can have your own choice of number of data copies to have a high resiliency, right? So that's all for the fundamentals of a distributed database. Let's jump on to replicas, which is today's main topic, right? So in what sense like people will use replica? So let me just give you a scenario. Like for example, right now you have one application first. You have a payment application. Then the payment application will have a backend database, like a single node database. Then the payment application will read and write from this database, right? Then later on, after some time, you want to build another app, but just to display the payments. You want to build a dashboard to display the payments. Then you're actually connecting the same app. Connecting the app to the same database node. But for the dashboard application, it will just issue the read-only queries, it will only issue selects rather than for the payments, you have insert, you have update, you have delete. But for dashboard, it will only issue read-only request. So two applications can use the same replica node, right? But what happens if you have more and more requests from the read-only application, like the dashboarding application, until the point that the single database node cannot handle it, right? So in this case, what you're gonna have is you're gonna have another database node which will asynchronously replicate the data from your original database, which will only issue the read-only queries from your dashboard. You may have a third application, like you want to do reporting. Similarly, you will just asynchronously replicate the data from the original primary database to what we call the replica node, right? So this is the first use case when you want to offload some of your read-only request. So take note of this is a read-only request for your read-only replica node, and the data replication between the nodes are asynchronous. And then there are second type of scenario, like same as before, you have a payment application, you read and write to your single node of database, then you have another database node, like to replicate the data asynchronously bidirectional, right? But you are not using this node. So in the event of failure of your primary node, so this read replica can be promoted as the primary node. So your application, your payment application can continue to read and write to the database. So to make sure the downtime are minimized, right? So these are the two typical scenarios or use cases why people tend to use read replica. So one is very obvious. You want to offload some of your read-only workloads, right? So the key point here is read-only, and the other is for fault tolerance. For instance, for example, your one of the node goes down, there are other nodes to continue to take over the traffic, right? So to implement the read replica in database world, there were multiple ways to do it, from the original monolithic database, single node database, to distributed database. There were multiple ways you can replicate the data. So first, you can actually use the block level storage replication. So you're actually replicating the data on the storage level, something like a RDS multi-AZ design or SIGN replication. For this case, even though they can replicate the data like this, initially for RDS multi-AZ, this node is a code standby. It's not used for read-only requests, but with the latest version of RDS multi-AZ, you can actually use this node for the read-only request, so-called treat it as a read replica, right? So this is the replication happens on the storage layer. The other way, which is more common, it is actually happening on the log layer, on the database layer. So for when your primary replication is read and write to your primary database, there will be write or head log generated. So you will ship the log over to your second database node, then replay those logs, right? To make sure the data is consistent. Then your read-only application can connect to your read replica node. So these are what we call, these two options or architecture are what we call the single node kind of architecture. But for a distributed database like YugabyteDB, it takes a a completely different approach because the data is actually sharded into multiple pieces and placed in different nodes in the cluster, right? So for every chunk of data, there will be a leader and there will be two followers or more followers as you defined, right? So you can actually read the data from follower to serve the same purpose of your read replicas within the cluster itself, right? And this data replication is actually synchronous and governed by the rough consensus algorithm. And this is actually built in within the database itself. You don't need to rely on middlewares or any third-party tools to handle the database, the data replications, right? So on the left-hand side is what we normally call the single node architecture. And on the right-hand side is a distributed architecture. So in the distributed architecture, there were two ways in Yugabyte you can actually achieve the read replica. The first one is what I mentioned just now. So you can actually, since for every piece of data, you have a leader and you have multiple followers. So you can just read from a follower in the same cluster, right? In the same region. So in this way, we call it follower rate, meaning you are reading from one of the followers to have the still rate. The other way, or the other use case, like what if your primary application sits in region A and you have another application sits in region B, but you still want to read the data? So in this case, there's a dedicated, the node will be serving as a read replica in the Yugabyte, but these are actually within the same universe, or we call it cluster. So the replication is done through the rough consensus algorithms, right? But the node here is not doing the voting in the raft. So it just receiving the transactions or receiving the data. So this architecture is what we call the remote read replica. So by using these two ways, you can achieve to serving your read-only request can be in the same region, can be in a different region to have a lower latency, right? Just to do a quick comparison between the traditional way of read replica and the distributed way of read replica, what's the difference between these two? So it comes with two aspects. The first is if for the first architecture, like if you're using replicating the var log, the single node architecture, the second node, the node 2, will actually has a complete copy of node 1, exact complete copy of node 1. And for node 2 itself, it has its own system catalog information, its own connection pool and all this. So these are all independent, right? On the other hand, for Yugabyte, just now we talked about T server and master service. So the master service actually holds all the metadata, including the system catalog information. So if at the remote location, like in region B, if the database connection is established, it actually needs to fetch the metadata, which is stored in the master service in the primary location in another region, right? So there will be some delays. And the second way, the second aspect is more from the disaster recovery point, right? Originally, if a single node kind of architecture, since the node 2 has a complete copy of node 1, and when the node 1 goes down, you can use node 2 as a DR, right? But for this case, in Yugabyte case, if you are connecting to the read replica node, not follower rate, if you are connecting to a remote read replica node, it's not really a DR solution, meaning that if your primary region all goes down, this node will not be able to continue to serve the request. So if you want to achieve the DR in Yugabyte, there's another architecture you can adopt, is what we call the X cluster replication. So meaning that there are two regions. In each region, you will set up a Yugabyte cluster. Then you will use an asynchronous X cluster replication to replicate the logs and replicate the data. All right. I see some questions. Why do we need bidirectional replication for replica? Any specific? Okay, Yugi will answer those later. Okay. Then I will just continue first. So read replica in the distributed nature. So just now we talked about this architecture. So just bear with me to follow the process, like how we actually update, write, and read in the distributed fashion, right? Like your application will update the record in one of the tablets. If you issue like a update table and record, etc., then this request will be routed to the master service to get the latest, the tablet location, leader location. Then it will redirect this request to the leader. It will commit on the leader. Then it will sync the update to the two followers via the raft, right? Then it will wait until one of the follower replica to append the commit in the log, right? Then it will tell the client, right? Only after the majority of the copies have been committed to the cluster, then it will tell the client your commit is successful, right? So you can see the process where when you need to go to the master service to get the metadata. So for follower reads, generally your read and write, all your reads and writes will only go to the leaders, right? But if you can sacrifice the freshness of the data, meaning that you may not read the latest data, but you can have the stale read, for example, for maybe 5 seconds, for 10 seconds, or even for 1 minute, then you can read directly from the follower to have a much lower latency. This is especially used for, right, if you have some read-only services or applications, right? The other way is what we have in the remote deployment of replica. So leader, follower, and the candidate are the original three so-called the role in the primary cluster. So the leader is a single reader and writer to replicate the logs. It will also replicate the client operations to followers, right? Then the follower will just accept the operations from leader and persist the replica of the log. And in case the leader goes down, right? So the follower will go into the state of a candidate, and it will propose an election of the new leader, right? One of the follower will do that. And in the remote replica setup, we invent this new role called observer. So similar like the follower, it will also accept the operations from the leader, right? If leader commit one record, we will also get the record, replicate the record to the observer node. But this observer will never participate in the voting or writing or becoming a candidate or leader, right? So that's why when your primary site, like all your leaders and followers are gone, you won't be able to use the observer, right? So this is a typical architecture of replica. For example, you have a primary cluster in the US. Then if you have another deployment, application deployment in Australia, then you can have two replica nodes in Australia. And for the replica node in Australia itself, it will serve the very low latency reads to your applications. But just to take note that this replica cannot be used for fill over for your in case your primary goes down, right? And in Yugabyte, because of our previous design and the architecture itself, we did make some improvement for the replica performance and best practices. For example, we have the smart driver. I mean, initially let's take a Postgres example. If you have multiple nodes, then if you want an application to connect to these Postgres cluster, then definitely you need, for example, whether you need a load balancer or you need some third-party middlewares like HA proxy or other components to do the traffic routing, right? So for us, we actually write a smart driver, which is built on top of the Postgres driver. So what it does is it has the cluster awareness. So you don't need a load balancer right now. So the application knows where to connect which are the available nodes in the cluster, right? And it is also topology aware, which is very important. For example, if you going back to the previous architecture, you have a primary cluster in the US, you have replica node in the Australia. Then for your Australia application, you can in the GDBC URL, you can specify you only want to connect to the Australia database replica nodes so that it won't go all the way to the US, but it will just do the local reads, right? So the driver also knows where does the database node sit. It will go to the nearest one to fetch the record. Okay. So the smart driver has a load balancing capability. For example, once the load balance is enabled, if you have multiple database nodes, then the client request will be auto load balanced to all the database nodes. It could be spanned across multiple AZ or even multiple regions, right? And this is a topology aware, like you can connect to specify in the smart driver or GDBC URL, you can specify which region you want to connect to. And you can also give a number to specify the priority, meaning that if you specify C1 region 1 with the priority number 1, so the request will go to the region 1 first. If the region 1 completely goes down, that the region 1 is not reachable, then the request will go to, which is number 2, will go to region 2 for the request, right? Yeah. But this preference value is only optional because it has a fallback capability. So if it doesn't find the one with the number, it will just fall back to the all the other available nodes in the cluster to serve the request. Okay. And just now, when I talk about the master service, like for the remote replica deployment, you need to go all the way to the other region to fetch the metadata and all this. You will incur, for the application perspective, you will incur high latency, right? So this is the existing problem, especially like if you have a huge number of active connections, it will generate high pressure on the master node, and also the remote deployment will incur the latency issues. Like when the T server connect, all the T servers, they need to fetch the metadata from the master service, right? So we have made the improvement to cache the metadata into the local T server. So before, the system cache, you need to go to the master node to cache that. But right now, we have made this T server cache, so the request cache can be cached on the local T server. So you don't need to go, I mean, even though it doesn't cache 100% of the data, but as much as possible, it will cache the one that previously you have incurred. So it actually improves the latency, improves the performance especially when the database connection was initially set up, established in a remote deployment, right? So previously you were having kind of this architecture. Then after that, after you can cache the request cache into a local T server, so the Postgres backend will just connect to the to get the system catalog from the request cache, right? Okay, I think that's all I want to share. So let's see some real world examples from Airwallex. So I will hand over the place to Harry to continue.
Cool. Thank you, Ron. Okay. So I would like to share some experience we have learned and during adopting of YugabyteDB, and hopefully that will be helpful for everyone is planning to adopt YugabyteDB as well. So here we go. Let's go to the first slide. So let's give you some brief about our business challenges. Because as we know, as I mentioned before, Airwallex is a global business. Like our business, operate continuous globally and 24/7, and we don't have any designated maintenance window. We don't have the luxury to turn down our service for like a couple minutes to upgrade the database version, etc. And secondly, our data are highly distributed because, in order to comply with legal regulations in different locations, we must to maintain a localized data storage. This means any sensitive data like financial data, customer information, transaction records, etc., must be stored within a specific jurisdiction to comply with the data protection and privacy laws. And it's critical for the financial industry. And this requirement actually necessitates dispute infrastructure, like carefully manages data storage location to ensure legal compliance while maintain data security and accessibility. And another challenge we are facing is latency. Latency is very critical to Airwallex business because in our business, especially in Forex, FX world, the currency price ticks every second, or more frequent than every second. And any latency could mean loss of profit. That's definitely. And secondly, in some of our services like the card transaction acquiring and issuing, the vendors require us to complete the transaction in a very strict response time, like sub-seconds, in order to approve transactions. So basically, every time you tap your credit card or tap your not tap, but you use your credit card online, there's a hard requirement for our vendor like a Visa, Master. We have to complete the transaction, the response within a sub-second, which means the cross continent latency is not quite acceptable. When you think about the latency between US and Singapore may be like a 500 millisecond already, so we don't even have time to process any of our transaction. Okay, that's the major challenges we're facing. Okay, let's move on to the next page. So yeah, we have been using different data solutions over the years. We used Cassandra before. We got a lot of Postgres instances in the business as well. So for Cassandra, it's a very good distributed NoSQL database. However, there are some pitfalls really piss us off. The first one is the the query patterns of Cassandra is very closely tied to the physical data the physical data distribution, which means any change of your query, you may need to rewrite your table, migrate all the data around, etc. And for a rapid evolving business like us in a startup, it's not quite acceptable because our business requirement, our product changes every day. So we don't, the database just can't keep fulfill our moving our requirement of moving fast. And secondly, it's the transaction support of Postgres of Cassandra is quite limited. It's because of these issues we cannot use Cassandra everywhere because some of our service are required to deal with complex data integrity. So yeah, we use Postgres for those services in the moment. So, but for Postgres, it has its own pitfalls. To begin with, Postgres, it's has a single point of failure. If you want to upgrade your version, or fail over anything, it requires a downtime, requires a maintenance window. For us, the maintenance window is not quite acceptable, especially for the version upgrade schedule, the maintenance window required by the cloud SQL providers. Okay, so why did we decide to go with YugabyteDB? So there are a few benefit actually to adapt YugabyteDB from our point of view. To begin with, it's the compatibility, Postgres compatibility, because we have a lot of existing services are already on Postgres, and our devs has extensive experiences with the toolchain of Postgres. So it's important to offer a smooth migration path from Postgres to YugabyteDB. So that is quite critical to the success of adopting a new technology. The migration path or the that's the first thing. And for tolerance, it's quite important. With YugabyteDB, there is no single point of failure. There is no downtime or no maintenance window requires when upgrade the version of database or reboot of any nodes. It won't impact the whole availability of the whole cluster. And another benefit with YugabyteDB is the Replica cluster actually can provide pretty good low latency for if you need local data read. And there's no actual operational overhead, like setting up load balancers for all the read-only replicas. In Postgres, you can create a few read-only replicas, but you have to create your own load balancer in order to make sure any of those read-only replicas failed, your application still can operate without any interruption. And another feature we liked about YugabyteDB is the low-level geo-partitioning, the feature-proof feature. As I mentioned before, we do have the requirement to store data in different locations, different data centers required by the legal, and that's currently we implement the partitioning on our application level. So our application have to read and write from different data center in order to put together a full picture of some information, like you are a user, you have you have accounts in different different countries. So basically, we have to store all those account information in different data centers to fulfill the requirement. And if you wanted to have an overview of your accounts, we actually have to fire RPCs to different data centers to put together a full picture to render for you. And using a row-level geo-partitioning provided by YugabyteDB, we potentially can just move all those overhead to database, at least to the database engine, and will be transparent to our application. And the overhead of developing the services will be kind of reduced significantly. Okay, here's an example of how the low-level geo-partitioning architecture can benefit us. We have different data sit in different data center, and any query kind of cross data center can be like orchestrated by the database engine itself. To the application developer, it could be just transparent. You don't really need to know where's your data and what's the relationship, because all those relationship and data are managed by the database engine. Okay, I would like to share some of our existing deployment model with YugabyteDB. One of our application, it's called a configuration service. It actually stores the configurations like some toggles and some pricings in the database. And currently it's hosted by the Yugabyte cluster. We have cluster in Singapore as a primary cluster, and we have clusters in other data center like Hong Kong, US, Netherlands, because all those data are used to like approve transaction, like fetch your pricing, etc. So it's critical to have fault tolerance, low latency, everything. But the right latency actually is less a concern because the configuration doesn't change that frequently. So from this example, if you have an app located in Singapore, you can read write from Singapore master, and the smart driver actually will handle those load balancing to all those nodes to make sure every node will have even load. And if you have an app that a service app that located in Hong Kong, so it majorly should read from the Hong Kong data center to get the best result of the latency. So that will be the primary read. However, if the whole Hong Kong cluster is down, the smart driver actually can fall back to the primary to get the data. Is still available, but with a price of latency. The latency could be a little bit higher. It really depends on the network latency. And the smart driver actually will route the write to the primary cluster, which means in your application, the read write, from like local or remote, it's kind of transparent to application developer. We don't even need to know any details, anything about how the topology of the database. The topology of the database it's kind of transparent. Okay. So from this slide, I would like to share some lessons we have learned from adopting YugabyteDB, and I think it's quite important for everyone to notice that YugabyteDB is not 100% equals to Postgres due to its distributed nature. So to begin with, I would like to mention the tuning strategies of the planner, the query planner actually is quite different. In YugabyteDB, not just the data is sharded, distributed. The the index are sharded and distributed as well. So you have to be careful about how to choose the sharding key. You either use hash shard or range shard. It really depends on your business requirement. Most of the time, the default one, hash sharding, should be enough. But sometimes, if you wanted to query by time range, especially for the index, you should use the range sharding for the index, which will give you the optimal result. And John is another kind of performance hit in a distributed environment, because when you need to join two tables or two indexes, you have to transfer the data. I mean, the database Yugabyte have to transfer the data to a centralized place to do the join. So it could end up with a lot of network RPC and performance hit as well. So be careful about how you design the query, or change the sharding distribution to make sure it won't be a big problem. Because join a big table with a small result is fine, but if you wanted to join two big results from different index or different table, that could be a big performance hit. It will be a lot slower than Postgres, because Postgres can do all those joins in memory. And secondly, I would like to mention the connection initialization could be slower for YugabyteDB than Postgres, because it's distributed. It has a lot of metadata, or the database metadata need to acquire from different nodes. So it's suggested to use a connection pool to manage the connection efficiently. And another thing I would like to mention is about the caching. Ron just mentioned that Yugabyte already implemented some T-server caching, the metadata caching. That it's critical, to the latency. However, there are a few other cache we have to do on our application side. To begin with, it's the connection pool that I just mentioned. And secondly, we have to cache all the prepared statements. Otherwise, every time, the first time, not every time, the first time you use a prepared statement, you need to fetch all the metadata from different locations, and the latency will be quite big from our experience. So especially, you are using a connection pool implementation, for example, like a Hikari CP, it doesn't actually offer an easy way for you to warm up your prepared statements. So we actually, create an example to how to manage the prepared, how to warm up a prepared statements with connection pool that Hikari, by providing it with a data source instead of a connection configuration. In this case, we can bypass all those latencies for prepared statement. So if you guys are interested, you can go to the link to have look at the example I put together. So basically, it's how to utilize another connection as a parameters to initialize the Hikari data source in order to bypass the prepared statement caching. Okay, cool. I think that's all I would like to share. I'll give the control back to Long.
Okay, thank you, Harry, for the sharing. Guys, I think we got 5 minutes left. Are there any questions you guys wanted to ask? I think Yugi have answered quite all the questions in the Q&A. Any outstanding questions you guys have? Any feedbacks? comments? No? Probably I will just do a quick demo on the replicas so you guys have a better idea of how replica looks like. Okay. So this is the cluster that we created using a self-managed debug portal for Yugabyte. So I can actually create a uh, three node cluster as a primary cluster, then two replica node. So you can there's a map over here, so you can actually see how the cluster is formed up. So I have actually the three node primary cluster in Singapore in different AZs, Singapore AWS Singapore AZ1 AZ1A A1B and 1C. And I also have a replica one in Sydney, AWS Sydney, and another replica node in AWS US West in California, right? So you can also see the node status over here. Like these are the three node in the primary cluster and two replica nodes. So just to take note that for the replicas, you can actually fine tune how you want to have a high availability for your replicas. So currently I'm setting, if you want to see the setting here at the replica. So I'm having like two nodes for two replicas, which means each one of them will have a whole complete data, right? Whole complete copy of the data. Then if, let's say, if you have four nodes, but only two replicas, meaning that the four nodes will share the two copies of the data. For example, you have two nodes in Sydney, two nodes in California. Then two nodes in Sydney will share one complete copy of the data, right? So that's the things that you can tune to have the replicas, right? And through the portal, you can also see the built-in matrix and all this. So to create the cluster and replica is pretty simple, or it's GUI based. For example, you want to, this is a thing that I did just now. I create a primary cluster in Singapore across 3 different availability zones. Then at the bottom, then I just configure the replica at the same time, right? At the same time, I can configure replica. Then you can decide where do you want to spin up your replicas. It can be in Sydney, it can be in Tokyo, it can be Europe, Frankfurt, it can be, yeah. Then I can increase the copy. Then I can have California, right? So if I have 4 replicas with total 4 nodes, then each node will have a one complete copy of the data, right? I think that's all I want to demo here. Let's see if there are any other questions from the Q&A. Read. I see Warren is asking, a replica must always be another cluster or can never be just a single node. If I understand your question correctly, a replica needs to be another cluster. It can never be a single node because in the just now when I show the different roles, right? You have leader, you have follower, you have candidate, you have observer. So observer cannot exist on its own. It needs a leader, it needs a follower, right? You need a primary cluster to exist. Then you can configure a dedicated replica node. But if if it is within the same region, which means if you don't want to configure a separate RAID replica cluster, you can just use the follower RAID in the same region. The follower RAID just is actually reading from the follower. So you only need leader, follower, that's it, right? Then if a RAID replica will have a complete copy of the data, this means there's no sharding for the RAID replica. Yes, there's no sharding for the RAID replica. So there's no sharding for the RAID replica. Yeah, in short. But let's say you have two nodes, but you have one RAID replica, means that these two RAID replica nodes will share one complete copy of the data, right? So 50% will hold by one RAID replica node, the other 50% will be held by another node. Right. All right. So before you guys go, one last request is that we do have a feedback form. So if you guys can scan the QR code and tell us how do you feel about today's session, that will be great. And hopefully can see you guys again for our next webinar. Okay. And if you have any questions or whatsoever, you can also reach out to us through our community Slack, right? I will just give you guys maybe 1 minute to just scan the QR code to tell us how you feel about today's session, how we can improve. All right, I think that's all for today's session. Thank you everyone for joining today's session. Also, thank you our partner Harry for sharing your real world examples and experiences and best practices. Yeah.
Thank you, Ron. Thank you, everyone.
All right. Thank you, everyone.